Yes, you cannot.
That's the signal.
Wait, but you cannot live stream on Zoom today because there's the lecture.
No, I'm not streaming on my on.
Oh, on your okay.
I'll do mine and yes. Yep, I think we'll have a breakdown. All right.
Okay, we can start.
So excellent to have Antoine talking about really important stuff. But you're starting 10 minutes late, so we'll push everything 10 minutes later.
Okay.
Thanks, Antoine.
Well, thanks everyone for coming. I'm very happy to be here and to see you also. A few people in previous talks kind of bragged about how many of these 8 microstructure workshops they've attended for. At least it's the first that I'm. Okay, so it's the first time I'm talking there. And yeah, I will be telling you about this work that we've been doing with our esteemed organizers, Joseph and Nick, and the no less esteemed Rafael, which is a PhD student of Joseph that you probably all know, and Dimitrios, who was a PhD student and is now a postdoc in Ben Gurion University. And so I must say, to begin with, that all of these 4 people are more qualified than me, I think, to talk about this work. But okay, anyway, for some reason, I'm here to tell you about it. And okay, so let's get started. So okay, good. So the motivations for this talk is that as you know, the near horizon limit brain system is at the heart of holography. So we will actually review this example of flat discrete brains going to ADS 5 times S5. And currently there is an ongoing progress, as far as I understand, in systematic classification of solutions of the form ADS times spheres times something else, which adds up to the correct dimension. And with in mind the microstate counting, it's important to know what is the brain origin of all of this, because, for instance, it gives quantization conditions on the charges and so on. And so the goal, and that's explaining the title of the talk and the paper, is we want to zoom out from the horizon, because that's, of course, the near horizon limit. So we want to kind of go the other way. And given a supergravity solution of the form ADS times spheres times something else, we want to know what are the brains. And in this talk, I will be focusing on ADS4, I should have written times S2 times S2 times sigma, which would be a 2-dimensional strip. And these solutions have been worked out about 10 to 20 years ago by these papers, and I'm very happy that Kostas came, actually. So this paper is actually excellent, and I think there are 2. There's one in 2011 and one in 2012. And they really do a great job at describing all the details of these solutions. And today, the goal is to know what is the exact brain origin. And I will tell you in a minute what I mean by the exact brain origin. Because again, in those papers, there is really a lot is done, and the charges are computed, and brains are identified and linked to CFTs. But still, when I began being involved in this work, we noticed that some questions, at least to me, were unclear. And that's where I come to my motivations. So I've spent a lot of time in the last 10 years studying superconformal field theories. And for that, sometimes superconformal field theories can be realized as world volume of brain systems. So typically, this is what I will call a Hanani-Witten brain system. So the conventions for the whole talk are that the black horizontal lines will be the D3 brains, vertical red lines are NS5 brains, and the blue dots, they are brains which are transverse to the screen, and they are D5 brains. And when you have such a brain system, you can read out a quiver gauge theory from that. And quiver gauge theories, in turn, in 3 dimensions, define superconformal field theories. And these are the dual to the ADS4 solutions that I was mentioning in the previous slide. And well, my personal motivation in this is that I've been working with this brain system for quite a while, and there are a lot of things that you can do with them. So for instance, Hanani-Witten transitions, but this is always drawn in an absolutely non-back reacted frame. So all the brains are flat and orthogonal and so on. And so that's a zero coupling picture, but in real life, we are not at zero coupling. So the brains will deform in a certain way. And the question is, how exactly? And if we know that, can we identify where is ADS? where is so if there is ADS, there is a conformal theory, but then can we identify where in this geometry, like physically, in terms of physical coordinates, where is ADS hidden here? And it's a bit less trivial than in the case of pure D3 branes, which I will review in the next slide, because, well, now you have branes in all directions. And one of the key insights is what are these numbers that I've added here, the red and blue numbers. And we will see that this is the key in answering these questions. Anyway, so that's the plan. So, okay, let's first try the naive strategy, but then I want to first make the analogy with these three branes. So let me tell you what I mean. So when we have an ADS4 times S2 times S2 solution, we actually know what the branes are. And this is the drawing that I've put, but here I've put a slightly more precise dimension diagram. So we are looking at 1/4 VPS supergravity solutions that describe spherically symmetric intersections of D3, D5, and NS5. So they all have these three dimensions in common. So that's the three-dimensional CFT that lives here. And then the D3 brane extends in one additional direction, and the D5 in 3, and the NS5 in 3. And then when I'm saying spherically symmetric, is that I assume that these three are completely spherically symmetric. So this will be parameterized not by x4, x5, x6, but by u, which is the radial direction in these three dimensions, and v, which is the radial in these three. Now, so this is the brane system. Now, again, by holography, sorry, just by inspection, we have a three-dimensional n equal to 4. So that means 8 supercharges, world volume theory. And when you have this, the R symmetry of the theory is SO4, which is the sum of two SO3s. And I've kept the same color. So for all the talk, blue will always refer to D5 branes. So there is the coordinate U, and that's one SO3 in the R symmetry. And then the NS5 is red, that's V, that's the other factor of SO3. And we expect the dual to be of that form. So there is an ADS4, S1, S2, both are two spheres, and two additional coordinates. And so the whole point, the precise meaning of what I mean by their shape is what is the change of variable from one description to the other. So just so that, because we need to get this clear, here there are three real coordinates. There's Z, U, and V. This describes the shape of the branes. In here, we also have three real coordinates. We have the radial direction of ADS, mu, and then we have two real coordinates, or one complex here on this strip, so X and Y. And describing the shape is what is the change of variable that goes from U, V, Z to mu, X, and Y. And this is what we're going to do. Any questions here? Okay, so let's first do it for the simplest case. So let's forget about the 5 branes, just pure D3 branes. So that's the standard Maldacena holography. But then it's helpful to see where we're going. So if you just have these 3 branes, then the strategy is easy. You write the full exact solution, which is just the black brane. Then you take, you identify a scaling region. Where is the scaling region? Well, when you can neglect the ones, so you take R to be very small. Then suddenly you have this, and then this you can rewrite using ADS5 and S5. So this is the three-step process, and we want to mimic that. One last step here, if I take just these 3 branes, of course, it's a 4-dimensional theory. So it's I have an ADS5, and I want to write this ADS5 not as ADS5, but as a fibration of ADS4 over a 1-dimensional line in order to match with the language that I want to use later. So in order to do this, we can write the metric of ADS5 as there is a line parameterized by X, and this is the same X that it was in the previous slide. And then there is ADS4, which is weighted by some factor here. And then you can check that indeed, this is the metric of ADS5. And I've made this change of variable. So up to renaming the things, the solution to the question I was asking here, in the case of pure D3 branes, the solution is this. So let's look at what this is. Of course, since I have only these 3 branes, U and V are completely symmetric, so I can define R, which is the square root of U squared plus V squared. And then I can identify the coordinates. So these are the brane coordinates, R and Z. So Z is along the D3 branes, and R is transverse. And mu and X are the kind of holographic coordinates. So mu is the radial direction of ADS, 4. and X is the variable that I use to fiber ADS4 over the line. And so this is a very nice mapping. In particular, you see that R is proportional to mu and Z is inversely proportional to mu. So which means that the product R times Z is a constant, it's independent of mu. And this is what I will call spikes in general. The fact that there is this scaling, so one coordinate scales like mu, one like inverse mu, it means that there are spikes, which I've drawn in the next picture. So that's maybe not so clear what this is, but basically the blue line, so we are in the plot of R and Z, and the blue lines are at constant mu, and you vary X, and the gray lines are at constant X, and you vary mu. So constant X and you vary mu, you have these spiked things. These are the spikes that we will see all over again. But then at constant mu, you see that when mu becomes very small, then you get closer and closer to the brain. Remember, the brain sits at R equal to 0. So here, in a way, these are the stack of these three brains. It sits here. And then, the blue lines, when mu goes to 0, they kind of reproduce the shape of these three brains. So you can see the shape of these three brains with mu, and remember, mu is the radial ADS direction.
So what are you plotting?
So this is the line. So it's basically this change of variable. And I plot in the RZ plane the line of constant X and constant mu.
So different constant.
Yeah, exactly, a different constant. So this is small mu, and then mu increase, and then the gray is fixed X, but then and okay, already this plot, maybe it's not too intuitive to say this is just pure these three brains, but it's important to keep this in mind, because then I will do that for the whole brain system with the D5 and NS5. Okay, so this was of course the baby example. Everyone knows this. So now we want to do the same with the whole brain system. So the first step is find a full exact solution. Okay, so let's do that. And so here, I'll review quickly the framework. I think, again, don't ask me too much about the reference, because this is not really my field, but so let's call this the Lunin method, which is reviewed. And actually this thing comes from this paper with Anthony, who is also here, and Dimitrios. So the idea is, in order to find the exact solution for our system, we find a solution for another system, which will turn out to be related by duality. So this is an M theory, just intersection of M2, M5, M5 prime. So again, you have two common directions, and you still have Z, U, V. The difference is that U and V now are 4-dimensional, but you can still take the radial directions. And then, okay, you want to find an ansatz for that. And there is a natural ansatz, which is inspired by the intuition that the M5 are kind of heavy and the M2 are light, suggests to make an ansatz for the metric of that form. But basically, you take each of the factors and you weigh them with some functions. And here you use the fact that there is a fibration, so there is a non-trivial wrapping in the Z direction. Then you also have to prescribe the value, of course, of the F4 field. And I don't write the whole thing, so you have a whole bunch of functions, again, parameterizing this. And then you try to solve this. So first of all, you can use a lot of reparametrization freedom in all these variables in order to get rid of a bunch of these functions, A0. So all of these functions, A0, A1, A2, A3, and then there's a bunch here. They all are functions of three variables, U, V, Z. And well, then you can show, again, I don't go through the details, but you can show that you can set one of them to 0. And then in the end, you write everything in terms of only three functions, A0, A2, and V1. And then, so this is just reparametrization. And then you impose the Gravitino equation, delta psi is 0. It reduces to some equation like this, a first order equation. dz of something is du of something else. And then one way of solving this is to just say that, okay, this thing will be the derivative of some new function w, which depends on u/vz, and this is the other derivative. And then if you have this function w, then you solve the thing.
Right, and u and v were the radial coordinates and the two.
Yeah, U is around the D5 if you want, and V around the NS5. And finally, there is one more condition that this W. So in principle, W, you put any function here and it will solve your equation. But then you need an additional thing, which is the Bianchi identity for F4. And then it imposes that W actually can be written again as a derivative of something else. So that's the prepotential, G0. And it has to satisfy a very simple equation, but very complicated equation, which is this, it's a kind of Monge-Ampère equation with 3 variables. So again, G0 depends on 3 variables, U, V, Z. And well, this curly L is the Laplacian in the R4. And okay, that's a very nonlinear complicated equation for which, as far as I understand, almost no exact solution is known. But okay, provided you find solutions to this equation, you know everything. That's the analog of finding the exact solution for the D3 plane. Now, this is the M-theory solution, so you have to go back to our system, the D3, D5, and S5. And that's not too hard. Basically, you just smear along one of the arm of the direction of the R4, so for instance, like the U1, and you dimensionally reduce, you just forget about one dependence. And then for the other R4, you also smear, and then you T-dualize. Of course, when you do this, you've made a choice. You've made a choice to T-dualize along V and to reduce along U. So that choice, you could do the opposite, and this will be, in the end, S-duality in the resulting system. So after you've done all of this, I summarize this on this technical slide, but at least I wanted to have the metric here just to show that it's a bit hard. The summary of all of this discussion is, this is the exact solution. If you find a solution of the Monge-Ampère equation here, then from there, from this just G0, there is a bunch of formulas that tell you the whole solution. And okay, this is the metric, the dilaton, the C2, B2 field, C4, like everything is completely explicit. The problem, of course, is you need to solve this equation. And as I said, we don't have solutions to that. So it seems that in our endeavor to then solve and then look for the scaling region, we are kind of dead at this first step. Any question about that? So since we're...
Can I make one comment?
Yeah.
Lunin did an amazing job in this paper, because what he also did was he showed that that horrific looking equation by perturbation theory, you can actually solve it subject to boundary conditions. And he made a pretty good argument that there are always solutions. You lay down your M5 brains and just you can evolve the solution perturbatively. And it's well adapted because the right-hand side is quadratic and the left-hand side is linear. So therefore there's a sort of natural order by order perturbation theory. Anyway, just want to sing the praises of Lunin.
Yeah.
Remarkable job.
Yeah, don't hesitate to add comments and complete what I'm saying. But again, I view this topic from a very particular angle, so yeah.
It is, there's some simple asymptotics at large radius for this?
Yeah, well, that's what we're gonna find. Yeah, that's the point. So despite this complexity, there is indeed a simplification in a large radius, and that's where ADS lives. And then in the end, it will be these spikes, and we'll come to that.
Okay.
But before doing that, I thought...
Can I ask one more thing? Should I worry about the smearing and the T-duality, because a priori you have local brain intersections in type 2B, and the way you are doing it, there is a risk that I'm smearing things.
So we are smearing in, so here we are smearing along, say,
the smear and theory direction,
yeah,
that's
and
fine, but then you also smear.
Then you smear, say, X10, and then you
Yeah.
T-dualize. So then it's just that this M5 will become...
I understand the duality. What I'm worried about is local brain.
It's the work factors. The point is, if you smear and you T-dualize, you get exactly the good work factor. So if you take a D3 brain, you smear it and you T-dualize, you get a clean D4 brain, unsmeared. So to go to rank theory to type 2B, you smear twice, and then on one direction bring down, on one direction T-dualize, but then you get clean unsmeared brains activated.
Yeah, here that
The work factors come in the right way. So D3 brain, the Z is coming.
First, put the Monge-Ampère equation down, where it is. Yeah, he's doing something slightly wicked here, because he's got a function of 3 variables. The statement of that equation is actually true where if V is on R4 and U is on R4, completely generally. So that when you reduce, you can say, let's make it independent of U4, let's make it independent of V4. It's still true, this equation. And then it doesn't run into that problem. If you impose spherical symmetry, you're absolutely right, you get some kind of weird shit. But that equation, the second time that equation, it doesn't have spherical symmetry. It's actually
right. Yeah, of course. Here there is no spherical symmetry, otherwise you can. Yeah.
So you can put whatever spherical symmetry you like and whatever dimension, you can T-dualize the hell out of it.
Yeah, so that's the more proper one.
That's the
This is
correct
without imposing the spherical symmetry. It's wrong on the previous. Okay. So now I want to take a little detour before showing what Emil was suggesting, to try to still work hard and identify where the scaling is in this, despite the fact that we cannot find analytical solutions. I want to take a little detour through a pictorial solution. So we're not solving exactly, but we're making drawings. This is the thing that I'm used to. And actually, I want to start with something which is maybe not so familiar to you, but okay, that's the one way to me, which was clear to understand. So the whole point is we want to understand how the brains bend. And this is due to basically just an effect that the brains, they source a certain B field, and then the other brains, so say D5 sources a certain B field, and then the NS5 will be bent in that profile. But then one very easy way, if you don't know anything, and if you don't even know differential equations to do it by hand, is using not D5 and NS5, but D7 brain and say fundamental strings or maybe NS5 brains, it doesn't really matter. The only thing to know is that in this system, because D7 is codimension 2, the effect of the B field is really, really strongly visible. It's just a monodromy cut. And so basically, you define a monodromy cut, and then anything that is straight will actually be automatically bent because of that. And you can compute this effect by just applying a monodrome. That's why I
don't know how to read this picture.
So here, this is a D7 brain, one D7. And this is, if you want, an NS5 brain. So it's 5 brains that have PQ charges. And then you apply, in order to know what it happens when it changes across the monodromy, you apply a certain monodromy matrix, which depends on the fact
that it's the upper part going at 45-degree angle.
Well, that's just, you apply this matrix to this vector and you find this, and it tells you.
The brain.
Yeah, that brain's. Exactly. So there is, you could move, it's a geometric effect, which is, based on here you could move the monodromy elsewhere, but that would be cheating. And actually, I will come back to that. That would be putting all the flux of your B field in one direction. So if you want a monodromy, means you put all the flux in one direction. And actually, I will desingularize this by just saying I don't have just one D7, but n of them, or 2n, for it to be even. So and then the drawing looks like that.
That's a PQ brain at the top, the -1,1.
That's a PQ brain, yeah. So it could be PQ5 brain or a PQ string. It doesn't really matter. The effect is the same, yeah. But then you see that if you have a large number of those, then you can spread the monodromy cuts kind of evenly like that in an angular sector. And then you see that indeed a brain in the neighborhood of these 7 brains here just gets bent like that. And then if you want, you can even solve this thing. So you have a little recursive system here of the coordinates of these intersections. And then in the end, in the large n limits, you find some differential equation and it tells you what is the shape. So here, purely geometrically, this is again a high school exercise. You can find that there is a curve. And actually this equation is, we didn't find an analytical solution, but okay, you can, here the blue thing is the numerical solution to that, and it matches perfectly. So the idea is that the same will happen in our system. And but the nice thing is that we can solve the equation. So actually we will have an exact solution in that case. But here I like it because we can literally draw it without knowing anything. So let's try to do the same thing, but now with our system. So here I just recall the coordinates choices. And so now just to make clear what the setup is, we are not putting any D3 at the moment. We just want to see how a 5 brain is bent in the background of another 5 brain of the other type. So for definiteness, let's pick NS5. So I put an NS5 brain, N5 of them, at the origin of the UZ plane. And well, here now it's back to the easy land. We can write the explicit solution, exact solution. That's the solution. In particular, there is this B field here, which is non-trivial, and it threads the S1, the S2, the first S2. And now we add a probe D5 with asymptotics. So these directions are the asymptotics of the D5. But then we want to see how it is perturbed from the asymptotics. So the D5, we want it that at infinity, it sits at V and Z equals 0. So the D5 is at Z equals 0 and V equals 0. But then the shape is a function Z of U, which tells you what is the brane profile. And using similar arguments to previous discussion with the 7 branes in the cut, you can find that there is a differential equation, which is this equation here. Again, B and H5 are these factors from the previous slide. And the nice point is that we can actually analytically solve this equation, and equations are solved by this. So here, it tells you that Z times U is, there's the number of 5 branes here, and then there is some tangent, which makes the thing complicated equation. We still have no analytic function for Z of U, but there is this formula. And this psi 0 is an integration constant from this equation. So here I plot what it looks like for various values of this constant. So let's discuss a bit what's happening. If we take psi 0, this constant to be 0, then again, the NS5s sit here at the origin, and that's the D5. And you see the D5 tries to avoid it a bit. That's the effect. And you can see it of the same as the effect of the blast of the field sourced by the brane. But then this constant can be non-zero. So for instance, it can be negative. Then if this happens, then the brane actually has an infinite spike in one direction. If it's positive, but between 0 and pi, then the brane kind of goes like this. And then you see you can vary the value, and you can have the same going the other way. So what is the meaning of this integration constant psi? Well, the meaning is an effective number of these 3 branes. Actually, these pictures, we can interpret them as there being, so here there is no D3 brane, that's the pure situation, but as soon as this constant is non-zero, it's as if there were some D3 branes between the NS5 and D5s. And this is all summarized in this picture. So again, that's the solution without these 3 branes. We have NS5 and D5, and then if you do that, then it behaves like that. That's this curve here. But then sometimes you have an infinite spike. It's not the same spikes as the other one, but going here, it's like if these 3 branes end from the right. And then you can have solutions where the D5 kind of kisses the NS5, and that's amount to having a number of these 3 branes like that. If you are exactly at 1/2 NS, so the number of NS5 is N5, and if you have 1/2 of that number of these 3s, then the D5 is exactly straight. That's in a sense, the blast is exactly compensated by the number of these 3 branes with pools with the opposite strength, and then the branes are perfectly flat, and so on. So with this, again, this is a probe approximation. We've solved the NS5 background, and in this background we've put D5s, but it gives a good kind of pictorial way of seeing what's going on. We can learn a few things from that. Again, at the very beginning, I mentioned the Hannah-Newton moves, and you can actually see that it's demonstrated here in a sense. If you look at this situation here, NS5 and D5, and you look at this situation where NS5 and you have the same number of these 3s connecting them, you can see that the brane bends exactly the opposite way. So if you flip the picture in your head, hope you can do that, you see that this has a brane bend this way, but this can also be interpreted as this. So actually, from the point of view of supergravity, if you draw this non-back-reacted system or this non-back-reacted system, they actually both are the D5 bending this way. That's why when you do the non-back-reacted systems, you can exchange these 2 configurations. Actually, they represent the same geometry. And there is something which therefore is universal, which does not depend on you doing these things, which is, well, the shape here. But again, the shape, we've done this argument where nothing was back-reacted. But then actually the region that will be important for us is this region at the top here, where you can approximate the solution, and you find that Z decays as 1/U with a constant, which is just this psi 0, which is this integration constant. But I remind you that this was linked to this number of these 3 branes. So in the end, this steepness, so how the brain decays in a sense, can be rewritten using what's called the linking numbers in brain systems. So again, it's just a little rewriting of the thing. In the end, you have this linking number, which is the number of NS5s located to the left of the D5 minus to the right with a factor, and then the number of D3s. This combinatorial number is invariant under Hanani-Witten moves. It's the one combination which is the geometric one. And it gives you the steepness. So steepness and linking number defined this way are the same thing. So is it any questions on that? Okay, so then now, okay, this was really, again, the toy model. We just had one stack of NS5s and one D5. Now it's time to put all of this together and to try to solve our initial problem. So before that, I need to connect the, well, to just tell you a bit about what are the systems that we're looking at. Basically using D5, NS5, and so on, you can realize three kinds of physical systems, which are very, very different physically, but they can actually be studied using exactly the same formalism. And actually that was one of the nice thing of the paper of Kostas that I mentioned last time, the beginning, which deals with all of these cases in a completely equal footing. So what's going on here? By putting D3, D5s, and NS5s, you can have three situations. Either there are no asymptotic D3s, which means in the end it's a bounded system in the Z direction. And then what you're describing is a purely three-dimensional theory. But you can also have these threes extending to infinity, for instance, this way. And then the picture is what's depicted here. You have actually n equal 4 super mills, which is the wall volume of the D3 brains. And then it's a boundary, which is a conformal boundary here, which is this red wall here, which is three-dimensional. And you can also have two different n equal 4 superior mills on both sides, and then a wall between them. And then that's called in certain cases, it's called the James wall. And what's important here is that if you are dealing with these brain systems, in the end, you can denote what is the brain configuration by just these numbers. So here, which denote how many brains end on which brain. So here, it's 2, 2, 2, 2, 1, because 2 D3s and here, 2 and here, 2 and here, 2 and here, 1. If you have the purely three-dimensional system, then you have two partitions. And I will actually now focus on this case for a little while. So let's see how it works. So the notation in the field theory literature is T sigma rho of SUN. So you fix n is an integer, and then you fix two partitions, sigma and rho of n, which have to satisfy some bound. So this rho hat, so hat means the transpose of the partition, and that's the so-called dominance order on partitions. If you want, I can explain more what this means, but okay, that's just a technical condition for the theory to make sense. And then the idea is that you can just depict the brain system as follows. So for instance, here, okay, this is the example. So you have SU9, so you pick n equals 9, which means you put 9 D3 brains in the middle. And then you end them on one side on NS5 brains and on the other side on D5 brains in a way prescribed by the partition. So for instance, if I pick row is 2, 2, 2, 2, 1, then it's what I showed in the previous slide. You end these 9 brains and then you decrease by 2, 2, 2, 2, 1. So you have these numbers of these 3 brains. And then the other partition is 3, 2, 2, 2. So you do the same on this way and decrease by 3, 3, 3, 2, 2, 2.
Sorry, or is there some moduli space?
So there is, okay, so this is what defines the CFT. Then given a CFT, you can have a moduli space of vacua, which is a continuum. There is a Higgs branch, there's a Coulomb branch, there's an Higgs branch, and so on. And actually, the good theories, this is what I'm going to say on the next slide, but the good theories, they are defined in a sense by the fact that there is, in this whole moduli space of vacua, which is very large, there is a unique point, which is the full CFT, corresponds to the full CFT. So it's a unique point. So in a sense, the CFT is defined uniquely by just this discrete data. And okay, then when you have this brain system, then you can play these games of doing Hanani-Witten moves. So it's glorified version of what I showed in the previous slides when you move one. So here you can move them. If you move all the D5s within the NS5, you can get to something like that. And then you read a quiver theory. So these are the gauge groups, and the framing corresponds to the flavor nodes, and so on. And you can, of course, always exchange electric magnetic objects. So you can also move the NS5 inside the D5s, and then you read what we call the magnetic quiver, which is magnetic with respect to this one, which is electric. So these moves are all allowed. But then what did we learn from the previous exercise is that supergravity picks one. You can do all these tricks with brains, but in the end, there is only one geometry. So what is the geometry? The geometry is the one where the branes are ordered according to their linking numbers. So this linking number that we define, which is the steepness, the linking numbers can be, well, I didn't copy the formula, but this was the formula with number of NS5s on each side and so on. You can compute them. And these are the red and blue numbers here. You can trust me that these are the numbers. And you see that here, they are not ordered by increasing sides. They're 0, 0, minus 1/2, 0, plus 1/2, 0, 1. In the other side, also they are not ordered. But you see that they are the same. So linking numbers are preserved when you do these moves, which means it makes sense to order them in a unique way by linking numbers. And so if you do this on either of those brain systems, you find these things. You have the 3 minus 1/2, they go here. Then you have the 4 zeros, they come here. Then you have the plus 1/2 goes here, and the 1 comes here. And then from our heuristic argument from before, identifying linking numbers and this bending, you can deduce that this is the actual shape of the brain system. So you see that the bending, so these numbers, the red numbers, there are 4 zeros, which means 4 brains are perfectly flat. And there are 3 minus 1/2, so these 3 go a bit like that, to the minus direction, and so on. And they thread in this way, never crossing. The fact that they don't cross is actually related to the fact that the theory is good. This is this uniqueness of the superconformal points on the moduli space of that. So yeah, I just wanted to make these points more clearly here in the slide. So when you have a quiver theory, it defines a CFT in a quite non-trivial way, because in 3 dimensions, the Yang-Mills coupling runs quite fast, and it goes very quickly to infinity in the infrared. So you need to be able to track, when you define your gauge theory, you need to track the degrees of freedom down to the infrared. And the whole point that this kind of demonstrates, and that's really did I cite? Yeah, I probably cited Gerrit-Witten here somewhere. Yes, here. So in these papers, and well, many others, they understood that there is this class of good theories for which this flow is particularly nice. And actually the flow just washes every detail of the theory. The Yang-Mills coupling is not marginal in 3 dimensions, like everything, masses and so on. In the end, you just are left with this combinatorial data, these linking numbers. And supergravity sees that, because the only thing that is left at the end is this bending, these steepness numbers here. So we will connect now to the supergravity solution. So these are the motto. The good theories are those for which the flow is most tractable, and the data is completely contained in a discrete parameters, which are these linking numbers. That's what's said here. And if you try to do the same with the bad theory, so bad theory, well, I haven't really explained how to construct a bad one, but for instance, if you have a UNC with a number of flavors and the number of flavors is too small, then if you try to do our heuristic construction, then you will end up with brains that want to cross. And that's a sign that something is wrong, or at least that the flow is not so easily tractable from the UV to the IR.
Talk about supergravity across
oh, no, because I well, maybe you
can interpolate a comment. Supergravity absolutely hates it when brains cross. Say that supergravity approximation breaks down. So supergravity is absolutely prejudicially bent on finding things where brains don't cross.
Yeah. Moreover, brain crossing corresponds to cyber duality. So when you think of the brain dissections in the brain dissection, crossing brains actually corresponds to cyber duality in the theory. So basically, this is so what this is saying, that it's back to the bad configuration, put brains the wrong way, then they cross, there's a cyber duality, there are degrees of freedom in the intersection, in the theory basically close to the cyber, to the good conformal phase, which is the one which is always the good one. So bad configurations always cross themselves, and at the end they always go, when they go towards up, they always go to the good ones.
So if you do pure UN, for instance, that's happening.
Does that correspond to doing some sort of duality transformation in the supergravity, like locally the intersection?
I think it really is a string of it all.
Spring, so this geometry is just strings.
Supergravity cannot, certain brains can cross and then strength of it, but supergravity hates that then because it does every string and then crossover. So
So Cleveland structure, for example, has standard duality, and if you look at the Cleveland structure, realize your brains, the brains cross. But then, if you look at supergravity, standard duality also has supergravity in the world. But it's a much more complicated world. Some fields that depend on the position, and the exchange, so it's a different. So supergravity can do standard duality, but somehow not at this level.
Yeah, the thing was, of course, this drawing, I should really have put some quotation marks around that. This is kind of a cartoon. This is what would be suggested if we could trust what we've been doing before. But the problem is precisely because they hate to cross, and we are in the probe approximation and so on. So this picture is really not what is physically happening. It just signals that there is a problem, and indeed there would be. But this is actually what these good theories are. As I said here, this is the good definition of what good means. It means that the flow is easily tractable. If the theories are bad, it doesn't mean that they are bad. You should not study them. Actually, they are very nice theories, but they are just harder. And the brain systems and the supergravity solution would be harder. And okay, we have to work more. So, but in the end, because of this, in a sense, by construction, this is what I will show in the last part. Everything we can do is just the good thing, the good theories. It's almost by definition.
So you said the good, the bad. Which one's the ugly?
Yeah, then there's the ugly. So the ugly is kind of the same as bad from the supergravity perspective. The reason why it's there is a trichotomy and not a dichotomy in field theory is because the ugly ones, in a sense, they are those which are almost good in the sense that this property of having a unique point in the moduli space of vacua, which is superconformal, is almost true. Actually, what's happening is there is just a one or higher dimensional slice, but a very easy one. So if you want, I can tell you more about the geometry of the moduli space of vacua, but that's a distinction. But that's, to my understanding, as far as supergravity is concerned, ugly is as bad as bad. Okay, so now it's time to finally get to the near brane geometry and to review this construction by using the formalism of Docker and company, Estes, Good-Curly, and then Costas with Benjamin Hassel and Estes and Gomis. They have described a very large class of ADS4 geometries, and they have been able to match them with the charges of the brane system. So let me quickly review this. Again, it's also a bit technical, so I will be a bit fast. The idea is, remember, the geometry is ADS4 times S2, S2, and sigma. Sigma is this strip, this yellow strip here. And on this strip, there will be harmonic functions, two of them, H1 and H2. And they satisfy some particular boundary conditions. In particular, H1 vanishes at the bottom and H2 vanishes at the top. But then both H1 and H2 are allowed to have, so they must be harmonic on the bulk of the strip, but then on the boundary of the strip, which is not included, they can have poles. So typically, okay, that's an example. So H1 and H2, for instance, H1 has some behavior, and then you can see here, if you can decipher this, you see that there are some poles on the on this boundary here. Now, physically, what's important is that the metric, once you have this function, the metric is fully determined. So the metric is ADS4, S1, S2, S2, and this is the metric of the strip. And then the factors in front, they are just very simple. I mean, not so simple, but there are some explicit functions of this H1 and H2, which I didn't write. But if you have H1 and H2, you have all of this. And again, the only requirement is that this H1 and H2 are harmonic and satisfy this boundary condition. So these are actually almost the most general class of examples that you can find. So you can take this and then plug into this metric, and then you find the whole solution. So the important part is, as I said, that there can be poles on the strip, and the poles can be interpreted as the presence of branes. what are the branes? When you can diagnose this by just looking at cycles in the geometry. And if you have a pole here, then you can encircle this pole with a little curve here, which is called, for instance, C2. And then if you take, what I didn't say is that one of the spheres, one of the two spheres, the blue two sphere is shrinking at this point because of these factors here, F1 and F2 and so on. And so actually there is a 3 cycle here, C2 times this S2, which is fibered over the whole thing. That forms a 3 sphere. And then when you integrate the F3 on this, you find a value. And that value is directly, basically it's the charge of the D5 brane, but that's basically the number of D5 branes.
So, but there was a previous discussion where there was a long interlude about the difficulty of solving some Moser-Ampere equation.
Yeah.
So now we just have harmonic functions.
Yeah, because now we are not so, now we are in ADS4. So we are already assuming it's a very different ansatz. Before it was R3 times R times R. And now it's ADS4. So you've already assumed that there is an ADS4. And then you don't need to solve the Moser-Ampere. And the point is to
join that into previous discussion.
I'm going to connect the two things. The point is to connect. So here I'm just explaining that if you assume ADS4, then you can solve everything. And you can even recover the charges of the D5 and S5 using the same argument here. And then for the D3s, it's a bit more subtle because the 5-form flux, F5, which is sourced by the D3s, satisfies an equation of dF5 is H3, which F3. And so if you want to find something exact, then you can either do F5 minus F3D2 or F5 plus C2H3. And then you have to be a bit careful of which one you're taking because not all of them are regular on the different boundaries. And it turns out that the two things which are well defined are these D3 page charges, which are not just the integral of F5, which would be not quantized and which would be kind of gauge dependent, but these particular quantities. It turns out that these page charges, if you evaluate, so if you plug into these H functions and you evaluate all of this, you actually recover a very good approximation of the linking numbers. Actually, you find the linking numbers. So, okay, that's just a long change of notation to say that the number of D5 and the charge are the same thing up to some factors and so on. But you have to, if you work out all the factors precisely, and that's what was done in the papers by Costas and company, you find in the end that the ratio of number of D5 by number of D3 by number of D5 define this Li. And this Li, you might not recognize them here, but they are exactly, if you look at these things, you have kind of this arctangent of exponential is really kind of step functions. So they really in the end count the number of branes that end from one side and the other and so on. And in order for these to be integers, the delta are the positions of the poles here. They have to be quantized in a particular way. So this is all due to the fact that we are doing the near horizon limit. But then really using this Li, you can connect now this to all the CFT discussions and the quivers and so on that I described, and then the brane systems. So now, final step was done. We want to connect with the very beginning where we had the full Lunin solution. And we can use all the intuition that we've gained doing the drawings and so on. The main point was that the C, remember the D3 along coordinates, when we made the drawings, it had a behavior like something inversely proportional to mu. That's just the scale. So we can say that there is an ansatz like that. And then we can plug this into the exact solutions and then match with the ADS4. And after doing all of this, it turns out that everything works very nicely. And actually, the algebra is not so hard. And what you find is this. So this is the answer to the question at the very beginning. This is the map between, remember, we were asking the map between 3 variables, u, v, z, and x, y, mu. And that's the map. H1 and H2 is basically a proxy for x and y because these are the harmonic functions. And so here you have on the right-hand side, you have x, y, mu. And on the left-hand side, you have u, v, z. And w, which is this 2 of variables. So yeah, that's the crucial, the central result that maps the different parts of the talk. And in particular, we identify, as in the case of the D3 brane, the fact that U and V, so the radial direction, they are proportional to mu, and Z is inversely proportional to mu. This was our ansatz. This is making this ansatz, so finding this is of course, we find this because this is our ansatz, but this is the thing that allows to reduce to ADS4. So that locates the ADS region. And in all of these drawings that I've made before, it means that we are zooming on the very high kind of the zone where the branes are bending in the universal way given by the linking members. Yeah.
So typically, some of these BPS systems, you get these nasty nonlinear equations, total equations, and you get these Monge-Ampere equations. But one of the things that seems to be universally true is if we find some clever way to reduce it from 3 or more variables down to 2, then that turns out to be solvable and often in a linear system. And so in this case, what we're doing is you had something god-awful thing which is a function of 3 variables, but you say, as I get near the brane intersection, there's a scale invariance. And the scale invariance is given by that mu dependence. And then that scale invariant coordinate becomes part of the ADS that emerges into the brane, and you're left with an equation now of 2 variables. And that horrific Monge-Ampere equation descends into a very simple linear system for H1 and H2. And in fact, one of the cool things is there are lots and lots and lots of ways of doing that.
Yeah.
But this is one of the cleanest and most beautiful.
Yeah, it's really remarkable that in the end, again, you just assume this and everything simplifies. Yeah, as Nick is saying.
Where? Zoom into the intersection of the branes.
Well, let's.
I'm ruining your thunder. I'm sorry.
No. It's good, but that's the crucial point. Where are we zooming? And the point is, in a sense, yes, it's near the intersection, but it's actually in the scaling region. So it's in the part. So remember when that's the reason we did all of this, is because the part which we can trust, where there is this behavior, is really around here and here. It's kind of a bit weird in this kind of drawings, but let me show some more plots.
You're sort of diagonally coming in towards the intersection.
Kind of, yeah. You can kind of think of the strip as okay. Let me show one more. Okay, this is one more drawing, and the reason why it's complicated is because in the end, in the U, V, Z, W variables, you really need more than one set of coordinates to define the whole thing. There is more than one chart. And that's why if you make a plot in UVZ, you're missing part of it. And here is the drawing. It's a bit hard to wrap your head around this, but let me try to describe it, and then we can discuss if you're convinced or not. So what these things are showing is the analog of what I was showing for the D3 branes at the beginning. At the beginning, I showed the plots. I don't want to go back at the very beginning, but there were this kind of U things. This was the plot as constant mu. And then when mu gets very small, it kind of kisses the D3 brane. What I'm doing here is the same thing. Is the mu constant images when mu is constant, and I plot this in UVZ and UVW patches. And there are really 2 patches which are mutually exclusive. So Z is always the transverse direction, and then U is here, and V, and same here. But now W is the. And you see, it looks very, very different. And the reason it looks different is, of course, incompatible in the region close to U and V equal to 0. It's only compatible in the scaling region, because that's where ADS is supposed to be sitting. So in the end, one way of representing this whole thing is that the brane, what the intuition gain with the brane system here is reproduced by these constant things. Remember, when mu is small, it kisses the branes. And here you can really see there is a fat thing here which corresponds to these 3 branes here. And then there is a small one coming from here. That's this spike here. And there is the same here. But again, we kind of have to hide behind this black cylinder the region where the solution is not well approximated by our harmonic functional zone, because that's only the ADS. So yeah, in a sense, that's the answer to where is ADS. So in the brane system, it's around here, and in it, it's around here. If you could solve Monge-Ampere, the whole thing, then you would be able to feel what's in below that. But still, and again, remember, this is mutually S-dual patches, so there would still be, I guess, I don't know what's inside here.
So in the original asymptotically flat geometry, what is the limit you are taking? I'm confused. You showed the ansatz for.
Yeah, so the limit.
What is the limit? So
So
what should I do with mu?
well, so mu is so the point is you are kind of if you want there is the full solution which is the nonlinear. Then you find an asymptotic region where it's linearized, and then you take this as the whole space. So that's why you can have some paradoxes like a finite discrete brane can look infinite in this space and so on, because you're taking a very small region and you're expanding it, and then you're so my vision of this is that in the original coordinates, so this is u, v, and z, you're taking large u and v,
Large.
yeah, or small z, which makes sense because we want to take the CFT limit. In the CFT limit, the z direction will be completely compressed. So you're zooming in here, and then you're describing the whole geometry there. But then it becomes, even though it's a limit here, so it looks like a two-dimensional thing, then you inflate it back to a three-dimensional with the radial direction, mu, which takes now the whole thing. So it's a bit, in the end, maybe drawings cannot really do justice to this, but in the end, it's just these equations.
It's very, if you only have one species of brane ending on another, it's very simple because you just get a set of spikes exactly as you can. So the top half of this picture or the side part of this picture, one brane ending on another always produces a set of self-similar spikes that produces a beautiful scaling region. The problem here is you've got D5s and MS5s, and the D3 zone. So you've got two species, and therefore you need the two patches to sort of see what's going on. And it's the bottom of your strip and the top of your strip, basically.
Yeah, exactly. If you want the strip here, we could kind of put the strip here in this transverse, so high but transverse, and then mu goes transverse to the strip inside.
So the black box is somehow the
yeah. If you make the black box very large, if you make the black box very
and you say when I flow, I don't see.
Yeah, you don't see the core. Of course, it's still only. I mean, it's obviously a partial answer to the original question. It's an answer only in the ADS regime because that's where we can match with them.
So you could imagine having a sum of different power laws. It's not scaling band, but like 1 plus 1 over r squared plus 1 over r to the fourth, and you focus in on the 1 over
Just
r
the
squared
first one.
scaling.
Yeah,
and there are two regions where the other ones come to dominate, and the black is where the r to the fourth dominates, and the other part is where the 1 dominates. So that's sort of, this would be.
Lost time. It's about how to interpret this.
But if you're talking about the vertical and the strip, it's actually much simpler. I think the strip and the component transformation, you will not the upper half plane, but the half upper.
Yeah.
Then actually in one direction you went to D5s, in the other direction you went to D5s. So it's see that these three popping up, opening up into D5s in one direction and then responding the other. So it's a simpler.
yeah. Maybe it's simpler.
Calculate, but there's one example in the we can actually do component transformation.
The picture back is that. So what's happening is that you should think about your strip as being sort of staying out of the black region, going from there to there.
Yeah, it's like here.
So you sort of found
That's the strip, and you have the poles on the top, the poles on the bottom here,
and the black region is where you fail scaling because it's doing some weird stuff bending around each other, and the other region where the scaling fails is when you go to infinity. The ones come to dominate in the harmonic functions of the brains. So if I dropped a spring to this thing, where would it want to settle?
maybe Demetrius.
Or are there a bunch of places where it wants to be? Where's the deep infrared?
Oh, but this is ideas.
Yeah, so.
For this, I mean, you see up the spikes in the 1 over r.
The spikes. They like to go up the spike?
Yes. That's very weird because I mean the field theory naively lives on the black. I mean, if you look on the right, the field theory lives on the black.
Yeah, it looks like it lives here, but actually, again, from this perspective, it's kind of not there anymore.
The lower degrees of freedom migrate from the intersection up to the spikes, and they only remember about the linking numbers. They don't care. I mean, the lower degrees of freedom, they don't care how the difference were, where they were. There's some linking numbers, they're invariant.
Yeah,
That's what the
this
lower
is my
knows, and that's basically captures on the side. In the sighting and all the other information, where the brains are, how we put them, and so on. That's all washed out.
So they sort of change around each other. That's not that part of the theory is sort of massive and integrated out. It's that universal scaling region that sort of folds around the intersections where there's light degrees of freedom.
To phrase Emil's question maybe a little differently, there is no limit in which I say five brain theory. F5 brain.
just 5 brains.
Yeah.
Not really.
Yeah, here with
not entirely. In theory, there's a way we capture this. It's an result for it. It's the fibrine, and you can put more on it. So there's a limit of the conventional solutions, but that's gamma limited gamma. Where it's the fibrine. Here in 2D, there's no gamma parameter in the sense. We cannot.
Yeah,
There's only
yeah,
one region which is captured. And I think it's linked to the fact that you cannot come back region also. It's a similar thing. You cannot plot the fibrine.
And it's essential to have some D3
But-
generating solution, just to get CFD.
I mean, in what we've done here, because we've matched with your ADS4, so you need these threes.
Yeah,
Then I guess
yeah,
if you could
but-
solve Monge-Ampere, you could solve it in a completely different direction where you would see the fibrine. It's supposed to describe everything.
Or probably regions, I don't know, regions in this space where the field theory is not conforming with this
Yeah.
and things like this. So therefore,
Yeah.
ADS4 will disappear in some of these things.
But that's why I introduced the ADS4 close to the end, actually, because to show that the whole beginning was independent, but at the end, we focus on that particular class. So anything that doesn't fall into that class.
But you say there should be a different limit where I see the linear equivalent theory of the fiber.
Yeah, this is supposed to be. Yeah.
Good question. There could be a scaling limit, but not in 3DS4 process 2 process 2.
Yeah.
Maybe some other scaling limit.
Exactly.
Like the negative gamma solution. Negative gammas are scaling next to them fibrines. The positive gamma are scaling next to them too. And so in essential, there should
But
be-
here you don't have that.
we don't do that. No, not in this ansatz. We don't do that. No.
Well, just as a general comment, that Monge-Ampere equation governs actually if you T-drawers every single damn brain intersection there is. And every one of these, I've worked it out now, every single one of those brain intersections has a scaling limit with different scaling powers, which then reduces to ADS plus S plus S plus units. There's a catalogue of about 20 of them we now have. But the one thing we haven't looked at, which is a really good idea, is the linear dilaton very for the story. There's probably will be a scaling limit for that. That's a really interesting thing. Yeah.
Okay, so I don't have so much to say in conclusion. This is what Nick was just saying. There's all the solutions of this. So, okay, what we have seen, just to get something out of it. So one thing which is very clear is that ADS4 emerges from the full solution from a scaling region. And the scaling is always of the type U or V scales like mu, and Z scales like 1 over mu. And then if you take X, Y, or constant and you scale with mu, these are the spikes. And again, these are different from those things which are these are the new constant surfaces. Then, as Nick was saying, this presumably generalizes to maybe all solutions of the form ADS sphere sigma. There's always a scaling limit. They always are scaling limits of brain intersections. And in our case, the scaling depends only on these linking numbers. And then we have identified from these 3 different frames the same integers, the Page charges, the steepness in the brains, and the linking numbers in the brain systems. And so this kind of settles the situation for this particular class of theory. It's quite large, but still, from my perspective, I've been studying this quiver and so on. This is quite small. These are those that in general, you evacuate at the beginning. You can say, okay, this we understand. So there are many more CFTs in 3 dimensions or other. So you can have quivers which are non-linear. I think we discussed some years ago whether they have what's their interpretation in string theory, but okay. You can take other types of gauge groups here, and then you can go into other dimensions to class S theories with a very large variety of punctures. I mean, there's really a lot more to do. So I think this is a very nice prototypical example of this kind of study. And I know that people here in the room have worked on many different aspects of that. But my perspective would be to try to do the same now that I feel like I understand at least one instance to try to see what's going on with the other families of CFTs. So yeah, I think that's it. Thank you. We're already a bit late, so
No.
maybe it's good to.
With 4 minutes over, that's pretty good by
Yeah.
our standards.
Oh yeah, because I had 10 minutes.
Yeah,
and,
you'll take it.
We don't have to say because
Yeah.
of this.
Any other questions? Stand count again. We can be in 20 minutes, so we say.
Yeah, so leave the Zoom open and we'll keep the YouTube going and
there
just
is
close
a-
your, oh.
No, it's Joseph.
Oh, it's you talking, okay.
I think you need to mute yourself.
So keep the Zoom open and we'll just keep the YouTube going and then we'll have
Did you,
we'll take it after. The next talk. Yeah, this room then for the next talk, yes.
And then we're in the other.
Let me move back. Start the video as well. Start the video as well.
Huh?
Video as well, yeah.
Oh, video.
Yeah, so that they see you.
Okay.
No, it's not. Good. And then share again.
Let's share.
Okay, one small announcement, Stefan Mistral is sick, and he's happy to,
Jumpstart the discussion.
but the thought is we have a discussion about BPS chaos or something.
In
like this.
principle, on one topic, I mean, he was planning to talk about that, but we'll have other topics as well. So the plan is after lunch to have a discussion of things we discuss, kind of, what is to be done, what's interesting, what are the questions which people are interested in, what should be answered.
So come with a question, or at least Stefan is going to talk a little bit, just introduce BPS chaos. I know nothing about it, but if you do, please feel free to jump in. But if there's something else you want to discuss, so come with the questions and we'll do our discussion. And then David will pick up it and finish the conference out. Okay, so
This is working,
have
YouTube is
here.
going, so.
recent progress in quantum gravity, fantastic.
Okay. Okay. So I will firstly thank the organizers for organizing this nice video conference and for inviting me. So also I'd like to thank all the speakers because I learned a lot from all the interesting talks. Okay. So today I would like to explain a few recent progress in quantum gravity. So this progress are made possible thanks to the following team of great people. So I don't think I have to introduce every one of them because I think presumably they are all very famous in our field. Okay, so also I should mention that I worked a lot with students at Harvard and UT Austin. So I didn't mean to create any hierarchy between students and the senior collaborators, but it's just very hard to fit all the photos in one slide. So yeah, that's why I separate them. Okay, wonderful. So the goal of the talk is to convey 3 messages. So the first message is that I would like to explain to you that most, if not all, of the problems in quantum gravity can all be understood in the framework of the Cartwright-Brane world. And also from the Antoine's talk, we see that the Cartwright-Brane world has a very natural string theory realization. Also thanks to the pioneering works from Kostas Bakas. And also, these considerations cause for attention from the string theorists to open the portal between quantum gravity and the string theory. So firstly, I would like to explain a few facets about the Cartwright-Brane world. So the Cartwright-Brane world starts from a very simple consideration. So what is the physics of an ADS-D brane embedded in an ambient ADS-D plus 1 spacetime, which is gravitational? Yeah. So here I drew this configuration in the concrete patch of this ambient ADS-D plus 1. So this green part is the asymptotic boundary, and the usual holographic z coordinate is going down. And this blue slice is a Cartwright-Brane. So the blue slice can live in many places, but a specific place is determined by the tension, which is a parameter of this brane. And then the geometry is ADS-D. Yeah, so this is the basic setup. So the question is that, what is the physics of this setup? So basic holographic considerations tells us that there are 3 equivalent descriptions. The first description is very simple. So we have a quantum gravitational theory in the ambient ADS-D plus 1, and then we embed a KR brane inside this ambient space. And then if we apply holography, then we can get an intermediate description, which is a second description. So in this description, we have D-dimensional ADS quantum gravity, which you can think of to be living on the brane. And then, but this quantum gravity is coupled to a non-gravitational bus. So that bus is that leftover asymptotic boundary. So this green part is the bus, and then this blue part is the gravitational ADS-D. So in that second description. And then they are coupled through transparent boundary conditions of matter field inside the ADS-D through this defect. And then so the energy flow is free to go from the ADS into the bus, or from the bus to go back to the ADS. So that's the meaning of the transparent boundary condition. And then so you can apply the ADS-CFT the second time to the ADS-D. And then you will dualize that gravitational theory on the ADS-D to a D-1 dimensional conformal field theory. And then, but the theory, in this green part is not touched. So therefore, you get the third description, which basically consists of this red dot and this green bus theory, which is a boundary conformal field theory. So yeah, so you have these 3 equivalent descriptions. So from holography. Okay, so for us, we are primarily interested in the regime where the bulk is described by semi-classical Einstein's gravity, where Newton's constant is very small. And then the brane is only parameterized by a single parameter, so which is the tension, roughly speaking, the energy density on the brane. So yeah, we are interested in this parameter regime because in this case, so the bulk theory is easily analyzed, and then so the intermediate description has a very strong quantum effect. Yeah, so this is the regime we are interested in because we want to study the quantum effect of gravity in this intermediate description, and then from the bulk description. And also sometimes we can understand that quantum physics also from the boundary description as well. Yeah, thanks to this parameter regime. Okay, so firstly, I would like to show you a basic consistency check of that equivalence between the three descriptions. So this is regarding the property of that gravitational theory on the brane, or the ADS-D gravitational theory. So that gravitational theory can be understood from the KK reduction of the bulk gravitational theory, or of the gravitational theory in the ADS-D plus one bulk. So if you start with a graviton of the ADS-D plus one bulk, and then so you do the KK analysis, then you will see that the lowest mode is not normalized mode because of the fact that so this direction of the geometry, which is perpendicular to the brane, so it goes from this brane to this asymptotic boundary. So therefore, this direction is not compact. So it has sort of infinite volume. So it tells you that that lowest mode is not normalizable. Therefore, all the physical modes are massive. Yeah. So this suggests that this bulk consideration suggests that the gravitational theory in that ADS-D is massive. Okay. So this property can also be understood directly inside this intermediate description. So in this description, this can be seen if you observe that. So there's a long range effect due to the leaky matter fields. So this tells you that there's some very light mode, which is absent. So in the usual ADS-CFD case, where we have reflective boundary condition, and it turns out that that light mode is like a Goldstone mode. So this is a long range effect, and then therefore there's a Higgs mechanism behind this ADS-D description, and you can actually calculate the mass, and then so you'll see that the graviton is indeed massive. Yeah. Yeah. So yeah, and also you can understand that from this third description. So in this third description, you have this boundary conformal field theory. So where you have a d-1 dimensional theory given this red defect, which is sort of dual to this ADS-D theory. So the graviton on the ADS-D is dual to the stress energy tensor on this d-1 dimensional theory. So that stress energy tensor is not conserved due to the coupling to this path theory. So therefore, its conformal dimension is not protected anymore. So then you can calculate the conformal dimension, and then you will see that it peaks up at a non-zero value. So that is dual to the ADS-D graviton mass. So therefore, yeah. So this fact that the ADS-D theory is massive can be seen from all these three descriptions. Yeah. So this is a basic consistency check, and then which will be important for us. I mean, so the fact that the gravitational theory on the ADS-D is massive will be important for us later. And then yeah. I just want to quickly walk you through a concrete calculation to give you some confidence that I'm not just brainstorming. Okay, so yeah, therefore I would like to explain a little bit detail about this dimensional reduction or the KK analysis I just mentioned. So to do that analysis, you start from this bulk description, which is given by this action. You have the Einstein's gravity in the ADS-D, and also you have the brane term, which is the second. Which is the second chunk of terms, and where T, the big T is the brane tension, and big K is a trace of the extrinsic curvature of the brane. As we explained that, we're interested in a regime where the bulk Newton's constant is very small. Therefore, you can analyze the equation of motion of this action. So we'll see that there are two sets of equations of motion. The first set is the bulk Einstein's equation. Then the second set is the brane embedding equation. So basically, you solve the first set of the equation, you figure out the bulk geometry, and then and then after that you solve the second set of equation, which tells you that how the brane should be embedded in this bulk. This is how it works. The case I'm interested in is this. The bulk geometry I'm interested in is this worked form. Yeah, the worked geometry, which captures the empty ADS-D plus one case. I think Antoine's talk also explained this. So where I just use a slightly different coordinate parameterization comparing with his talk. Yeah. So for example, if you consider ADSD plus 1 as the bulk geometry, then this exponential 2a rho is just Koch rho square or Koch square rho. And then so this J bar Ij, so which is a deep dimensional geometry is empty ADSD. Okay, so and then in this geometry, we'll see that so the brane is embedded in a constant rho slice, and then that rho is determined by the brane tension through this relationship. Yeah. So basically, you should think. So in this picture, you should think of this rho as this sort of angular or hyperbolic angular direction, which is folding this ball in this way. So there are many slices like an onion, and then so the brane is sitting in a particular slice determined by the brane tension. Okay, so we would like to do the linearized analysis of the graviton in the bulk. So therefore, we start from the linearized Einstein's equation in the bulk. Yeah, so H mu nu is the graviton field in the bulk, and then it transforms under the bulk d field in this linearized form. And then so I want to do the KK analysis. But it turns out that so to a proper if you want to do the KK analysis in fully covariant form, so it is better you consider some field redefinitions. So which is sort of overlooked in the original paper from Karch and Randall. So yeah, for that purpose, you should introduce this line field. So which is gravitational Wilson line. So in the case of gauge theory, this is basically the integral of A. Yeah, the gauge connection. This is a gravitational version. So you can see that this is basically some line integral of the bulk graviton field. So yeah. So yes, then from the d-dimensional perspective, this Vi is a vector field. And then this V rho is a scalar field. And then you also have to redefine this the sort of d-dimensional graviton field in terms of the original bulk graviton and this V. Yeah, so after that, you will see that. So this redefined field is transformed in a very nice way, which looks much more like genuine d-dimensional fields. Because, for example, this redefined graviton field transforms in this linear form. So which is like the graviton field in the d dimension, which transforms the same way in the same form of how the d-dimensional graviton should transform under the d-dimensional diffeomorphism invariance. And also this V field transforms like a simple shift. So you should think of this V field as a Goldstone vector field in the d dimensions, because you will see that the graviton is massive, and then there's Higgs mechanism, so therefore there's a Goldstone vector field. Yeah, and then also this V rho transforms in a simple way. Okay. Yeah, so as I explained, so this vector, this V field is just like line integral. You start from any point in the bulk, you do the line integral all the way towards the infinity in the rho direction. Yeah, so this is how you should visualize this object. And then so yeah, so you can just consider different components of the bulk linearized Einstein's equation. So you have the ADSD component, so which looks like this. So the first line is in the form of the d-dimensional linearized Einstein's gravity with negative cosmological constant, and then the second line after the KK reduction turns out to be the Fier's Pauli mass term. And then also you have this ADSD and then the perpendicular direction.
It's a mass, okay, because I see.
Yeah, so at the end it will become, use it. Yeah, that's right. And then so you have this second set of equations, and then this turns out to be the equation of motion. So from the d-dimensional perspective, this turns out to be the equation of motion of the vector field, of the Goldstone vector field. And then so you have this, you have another equation. It turns out that this equation is redundant with this equation. Yeah, because the d-dimensional linearized Einstein equation is basically traceless.
These are the same.
Yeah.
The two lines.
Oh yeah, you're right. Yeah, sorry. Yeah.
It's okay. It's a base problem.
Let me think. Yeah, you're right. I think this coordinate. Yeah, you're right. Yeah. So sorry about that. Yeah, just copy and paste it. Yeah, sorry. Yeah, they should be different.
Another one should be a vector equation.
Yeah, so this one should be vector equation. Yeah, somehow means this. Yeah, that's right. Let's see.
There's a type of probably copy.
Yeah, that's right. So there should be a nabla square vi, something like that. Nabla square vi as a vector. Yeah, anyway. Okay. Okay, yes. Yeah, so to perform the KK analysis, you can see that so this differential operator, so some power of the warp factor and derivative, and some other power of the warp operator and the derivative, and some power. So it appears in all these three equations. And then so therefore it tells you that you should think of this differential operator so as like the Schrodinger operator of the KK wave function. And then so the spectrum of this operator is a KK mass. Yeah, and then yeah, so the boundary condition of the KK wave function is given by that. Yeah, which you can work out from the variation of the bulk gravitons equation. Okay, yeah, so this is the correct equation. Yes, so yeah, so therefore you can consider a particular KK mode, and then so you just plug in yeah, just plug in the solution of the KK wave functions. You have these three set of equations. Yeah, so you can see that. So this one is a linearized Einstein's equation with fierce polymass, and but it is in the covariant form. So therefore I have this additional V part, and then this equation is actually the equation of motion from the V field. And then so this equation is redundant with that because linearized Einstein's equation traces. You can take the trace, the first line vanishes, the second line reduces to this. Therefore, this is redundant with the first. So you only have this two set of independent equation of motion. Yeah. So yeah, so this tells you that so the gravitational theory on the brane is massive. Yeah. So and the mass term is in this nice fierce poly form, and which is covariantized because of this V field. Yeah. Also, you should understand this V field as this line operator will start from the brane and then it goes all the way to the asymptotic boundary through the bulk. Yeah. So this will be important for us. Okay. So all these equations can be directly derived from the intermediate description. Yeah, but you have to do some hard calculations. So if you're interested in, I encourage you to look at the papers. Yeah. Okay, sounds good. And then so as Anthony nicely explained that, so this setup has a very nice string theory uplift or embedding. Is basically considering this system. So this system in type 2B string theory or supergravity, you can engineer boundary conformal field theories and then look for the supergravity. Look for the solution of the supergravity equation of motion with all these brane sources, then you can get this geometry. Yeah, so this ADS4 times S2 times S2 times the Riemann surface geometry. Yeah. Yeah, so the basic picture is like this. So near the brane, you have this ADS4 cross M6 regime. So yeah, which looks like a Scottish backpack. So yeah. And then so yeah, this part is glued to an asymptotic ADS5 cross S5 regime. And I think this part is called the quantum gate to another universe from the Costas work. Yeah, okay, great. Any questions?
Just one thing back there, so can we go back to the blue stuff? So essentially the non-compact region is ADS5 process 5.
Yeah.
The graviton, the ADS5 graviton is leaking there. But why isn't I mean, I just don't understand the ADS4 theory. Why is the graviton massive? I mean, you know, I mean, I just don't understand. I mean,
the normalizable graviton, because
Yeah.
you know, the
Oh, so there's a
ADS
big-
throat is infinite. so
Yeah,
you
the zero mode is not normalizable.
I see. And the next one also behaves like a graviton. I see. So you're saying all the, so this is the next KK field, or maybe not the next. I mean, it's in the KK tower.
Yeah. So
I see.
the masses one is not normalizable, therefore it's not dynamical.
I see.
Then you start
The
with
dynamic-
massive
the
one.
lower dimension.
The
Away
wave
from the lower
function has to go to zero inside the throat somewhere. Otherwise, if you have constant
Mhm.
wave function, which is the massless.
Graviton. I see.
Is
That's
it
low. I mean,
not
it has infinite volume. Okay. I see.
Yeah.
Okay. And then the mass is given. I mean, the mass can be computed from in the setups in some.
Yeah, just do that KK analysis.
No,
Yeah.
but you know, if you do it,
Yeah.
I mean, no. Here I see. No, but you know, in the
In the string theory,
to be
yeah, that is Costas work.
Okay.
Yeah.
Okay.
You can do it on the limit where the mass is not too big.
Mhm. And can we get the mass to be small enough by cramp? You have to get the mass to be small enough. You need to cramp
Yeah,
up the
but
number
by
of brains.
squeezing the throat. If
Squeezing
you
the throat.
squeeze the throat,
Oh, I see. So you have like 3D brains ending up with 15 gazillions and 5s and NS5s and D5s on top of each other. I'm giving this big
yeah,
fat
but
ADS
those
before.
that go, the semi-infinite ones can be few, and
Few.
then the mass is small.
I see. Okay.
And if you switch them off, the mass is zero.
Zero. Okay. Very
Yeah,
good.
yeah.
Very good. Very good.
Yeah. Okay. Wonderful. Okay. Okay. So now I would like to explain a few applications of the Cartesian-Operan work because I think now you're all experts in the Cartesian-Operan work. So yeah. So hopefully this can inspire you to come up with your own applications. Yeah. So each of these applications turns out to the calculations associated to each of them is actually a little bit complicated. Therefore, I would like to skip all the details of those calculations. But then I would like to tell you also the physical intuition, how we crack these problems. And then so I show you the results. And then after that, I want to explain to you the physical implications of them. And then so I will conclude after that. Okay, sounds good. So the first application is, of course, the famous calculation of the page curve of black hole radiation. So for that purpose, you can consider an internal black hole inside the ADS, just for simplicity. Of course, you can also consider the honestly evaporating black holes, but that will be a little bit more complicated. And then and the Cartesian realization of that is not very clear at this point. And so therefore, I would like to consider the simpler version, so which is a Masure's puzzle. Yeah. So for that purpose, you can start with a gravitational ADSD, which is living in this eternal black hole spacetime, and then you couple this gravitational theory to these non-gravitational baths, so which are like these shaded green regions. And then so you can consider the time evolution as denoted in this figure, and you can see that if you go to the late time Cauchy slice, if you go to the late time Cauchy slice, so the bath part will capture more and more radiation from the black holes. Yeah. So and then so you can study the radiation from the black hole by studying the bus directly, and the bus is non-gravitational, which is basically a QFT with some boundary conditions, of course. So which is much easier to understand than you study the gravity directly, because in the gravity it's not so clear how you could separate the radiation degree freedom to formulate this calculation of the entropy of the black hole radiation in a very clear form. So yeah, that's why we consider this setup. Yeah, so it turns out that if you do this calculation, and then so you are basically looking for the so-called entanglement wedge of the black hole radiation. So the black hole radiation is parameterized by bus subregion R, which consists of two parts, R1 and R2, on the two buses basically. So then if you look at the early time entanglement wedge of this radiation region R, then that entanglement wedge is R itself. So that tells you that, so if you know enough about the physics of R, you can only reconstruct what happens inside R itself. So therefore, there's nothing amazing happening. But if you go to the late time, so you'll see that, so the entanglement wedge of this radiation region R contains this disconnected part inside this gravitational region, so which overlaps the black hole interior. So therefore, now the entanglement wedge is not just R itself, but the union of R and this disconnected part inside the gravitational region. So therefore, if you know enough about this radiation region R, then you can reconstruct everything inside the black hole. So this is how the information paradox is resolved in this case. And if you do the calculation of the entropy, you'll see that. So this is how the entropy of the radiation depends on the time. So it initially grows, and then so the growing is cut off by this plateau configuration. So this plateau value is basically two times the entropy of the black hole. Yeah, because you have an eternal black hole. Yeah. So there are two entangled black holes. Yeah. So that calculation can be easily understood inside the Cartesian open world. So for that purpose, so you want to engineer a black hole on the ADSD brane. So how to do that? So you should start with a black hole spacetime or some black object, so in the ADSD plus one bulk, and then you embed the brane. So the brane will intersect, so here this dotted line denotes the horizon in the bulk. And then so this blue part, this blue line, vertical line is the brane. So the brane will intersect this bulk horizon. So therefore, there will be a horizon induced on the brane. So therefore, on the brane, you also have a black object which is radiating to this bus region. And then you can just calculate the entropy of this bus subregion R. So that can be calculated using the Ryu-Takanagi formula, because we considered the parameter regime of the bulk to be captured by Einstein's gravity. So it turns out that there are two different phases of the RT surface. So the first phase is that, so the RT surface can go through the black hole interior. So this is the first phase. It's going sort of straight down, but going through the black hole interior, and it re-emerges on the other side and then going to the other asymptotic boundaries. So yeah, so that RT surface gives you the initially growing part of the entanglement entropy of the radiation. And then you have this second phase, so where the RT surface ends on the brane. And this RT surface is time independent, so there's no time dependence at all. So therefore, at the late time, so the growing will eventually be cut off by by the switch of the dominance of the RT surface. So you have this brain ending RT surface which dominates at any time. So this is the Karl-Schwandel realization of that page curve. Okay. Yeah, so if you do the calculation, you'll get this exact page curve. And one question you might ask is that, why could the RT surface end on the KR brane? So the answer is really the replica wormhole. So yeah, so basically, if you consider the replica path integral of that entanglement entropy of the bath subregion, you'll see that. So there are two. This is in that intermediate description. So there are two phases. In that intermediate description of that path integral. So there are two phases of the saddle. So the first saddle is this ordinary saddle. So in the second phase is this replica wormhole saddle. So which connects all the copies. So yeah, so the replica wormhole saddle corresponds to the ending RT surface, and then this ordinary Hawking saddle corresponds to the going through the interior RT surface. And two quick comments are that, so in our work, so this replica wormhole is explicitly realized. Therefore, it is no longer a proposal. So as from the previous works or from the early works. Yes, and also we can directly derive this replica wormhole geometry from the BC boundary conformal field theory description. Yeah. So so that work is done in this paper. Yeah. So which I will also briefly talk about in the later slides. Okay. Okay. So just to locally summarize a little bit. So three implications. So in the Karl-Schwandel world, we have simple analytical models to calculate the page curve of the black hole radiation. And also, so a replica wormhole is not a miracle. So it is not an ensemble artifact as some of the people are trying to say in the community. And also, yeah, so the transition to the replica wormhole is just a generalized notion of the Hawking page phase transition. Yeah. So this is the implication from this work. Yeah, the replica wormhole is realized when the bulk is ADS3 in this work.
What does this mean? You mean simply a different saddle? Is this why do you say Hawking page? What does this have to do?
So I want to say that so it is not an ensemble artifact. Yeah. So Hawking page is true for any individual holographic CFT. It's not because of the CFT is an ensemble of theories. And then our work shows that so the transition has exactly the same mechanism as the Hawking page. So that's some details of this work. Yeah.
Okay, I guess I missed the main point. What does Hawking page have to do with the page curve?
Yeah. So I want to say that. So let's see. So you start from the boundary conformal field theory description, right? So you can study two problems. The first problem is the ordinary Hawking page transition, right? So you study the thermal partition function, and then you see what is bulk dual. So you'll see that so the bulk could have two topologies, and then this topology is encoded in some boundary data. Yeah.
I mean the ADS solid form as opposed to thermal.
Yeah, thermal the ADS. Yeah. So on the boundary, so they're encoded in the data. So like which cycle support the identity operator basically.
In this sense, basically.
Yeah, the same.
Two saddles.
Yeah.
Cross.
Yes, yes.
But for this, you need to build a black hole on the cut random black hole. I mean, you know.
So this is ADS3. So the bulk is ADS3. So the intermediate description is ADS2.
Mm-hmm.
Yeah.
But this.
It's very simple. It's very simple to do. Yeah. You just consider CFT to be in some.
No, I agree, but just in terms of the physical solution, if you can, to build this cut random black hole.
Yeah.
You need that.
Oh, I need that.
And that's something which people haven't built yet.
It's
really?
not really a black hole. I think it's this black funnel thing. Basically,
Yeah, black string.
two fibers.
Yeah.
You replace them by a black hole, ADS2 black hole.
Yeah, that's right.
I see. So that's not a real, but that's
So
not.
it goes all the way to the boundary.
But then the boundary has the same temperature as the.
Yeah, the boundary is
there
also
a
black hole.
thermostat
Yeah.
boundary.
It's a thermostat
Yeah.
on the boundary. So
It is
that's
different
not
from
really page curve. That's not really a code. What?
Well, it's a variant of the page curve. Yeah, Maldacen.
It's a variation of the page curve. I see. Because
Yeah,
for a page curve, I need the evaporation to happen on a cold bath.
It's not.
But to get a cold bath, I need to have a brain localized on the cut random brain, which doesn't extend all the way to infinity.
Well, not necessarily. As I explained here, that so in a genuinely evaporating black hole, you're right. You need a cold bath. But that hasn't been realized in Hartree-Randall. Therefore, I consider this setup where you have an equilibrium path, but you choose this weird time evolution which breaks this time transcriptional invariance. And then you look at the late time Cauchy slice, you see that the later time it captures more and more Hawking radiation from the black hole. Of course, you have some radiation into the black hole, right? But those are captured less and less on this late time Cauchy slice. Yes, you can just see that from
So
this.
there's a modified island
It's
scenario,
a
which is not, which is not like that, but okay.
Yeah, that's right. Yes. What I think what Costas just explained is that you can consider instead of this Minkowski bus, you consider bus to be another black hole. Yeah, but that black hole is not gravitational. Yeah. So that is realized by slightly different geometry than this. Yeah.
So the only caveat is that here you need a massive gravitonic theory. So I mean, to get all this islandization, to get all the realization quadrant, you need a massive gravity. It makes it to be as massive. I mean, you know, as little massive as you want, but it still needs to be massive. The moment it stops being massive, it doesn't.
Yeah, that's right. That's
Okay,
right. Yeah.
okay.
So as long as it is gravitational, the graviton is massive.
Okay.
Okay, wonderful. So that is my second point. That is my third point.
Okay.
Yeah. So the gravitational theory is massive. Thank you very much.
Oh, okay.
Yeah. Yeah. So just to clarify a little bit about this third point. So I think this graviton mass is actually essential for the existence or the consistency of entanglement island. So that can be seen by these considerations. So to see that, so let's consider a slightly simplified version of that intermediate description, where instead of a gravitational d-dimensional black hole, I consider an empty gravitational ADS-D. Yeah. So so then the setup is basically the same as before. We have this gravitational ADS-D, which is coupled to a non-gravitational bus, which is this Minkowski space on the right-hand side. And you take a Cauchy slice. And then, so you look at the subregion on this Minkowski bus, you look for the entanglement wedge. So you see that it will contain this disconnected part inside this ADS-D, basically due to the QFD entanglement between the ADS-D and the Minkowski. Yeah, so therefore, island exists in this simpler setup.
I've always been confused by this.
Okay.
Don't you need to be very precise about the leaking boundary conditions? I mean, how can you compute without giving a precise?
Yeah, that's right. You need a very precise leaky boundary condition.
The Ryu-Takayanagi surface can do various things when it hits the.
Oh, here, no. Yeah. So this is in the intermediate description. This is in the intermediate description. Yeah. So the calculation, the PR is done in the bulk. Yeah. So whatever this leaky boundary
is.
Yeah. Wait, did I draw it? Sorry. Yeah. So this is the bulk part. This is a bulk indication. Yeah. Just ignore this vivid line for a moment. Yeah. So this is the RT surface. It goes from here to here.
That boundary, okay, this is maybe it's not the venue for this, but that boundary is always confused to how I'm too, because it seems like it carries a hell of a big energy density, right? Why? Because you've changed the discontinuously the metric and the fields. There must be a massive amount of energy sitting there. Why doesn't it just fall into the black hole?
What do you mean? I don't understand.
Well, you've changed the metric discontinuously at this leaky boundary.
Oh, this leaky. Oh, yeah. That's right.
And you've also changed the fields discontinuously. So there must be some massive delta function energy on that surface.
Oh, I see.
So the question is, why doesn't that leaky boundary just fall into the middle of the black hole?
Yeah.
Yeah, well, let's say I think a simple model for that leaky boundary condition is to consider double trace deformation of this ADS-D theory.
I know, but I'm a gravitational physicist, and if I say
that is gravitational.
Stay around a black hole, I want to ask the question: why doesn't it fall into the black hole?
What does it fall into the black hole?
You know what? This is a general. I've never had a satisfying answer to that question.
Okay, I hope I can understand your question. But yeah, I don't seem to understand your question. But
Let's discuss afterwards.
oh yeah, maybe we can stop.
It's an interesting topic.
Yeah, sure. Yeah, that's right. As I just explained that you have this island part, which is this purple interval. Yeah, and then to see the consistency, to see the some consistency condition of the existence of island, so you can consider an operator OI. So inside this island, it takes some operator inside the island. So by the holographic interpretation of the island, so that operator is actually encoded in this bus, not on this not on this red vertical line. So which is the holographic dual of the ADSD if there's no bus. Yeah, so that is the holographic interpretation of island. So all the physics inside the island is not encoded in this holographic boundary or the holographic screen, some people would like to say, but it is encoded in the bus subregion. So you take that operator, OI, and then so that consideration tells you that this operator OI should commute with the ADM energy on this asymptotic boundary of the ADS. So therefore, it tells you that the standard gravitational Gauss law cannot be obeyed. So that suggests that the gravitational force can no longer be long range in the Euro sense. So it should be short range. So therefore, that is consistent with the fact that the graviton is massive. Yeah. Actually, you can work out the details of the constraint equations, which I will explain maybe in the last application. So you'll see that because of the graviton mass, the gravitational constraint will be modified. Yes, and that modified gravitational constraint allows the solution of this operator inside the island that commutes with the ADM Hamiltonian. And also, if you work carefully about that solution, you will see that that operator or that solution actually has a non-zero commutator with the bus Hamiltonian. So therefore, basically, that will the operator inside the island will excite the bus. Yeah. So which looks very amazing from this picture. Yeah, because so naively, if you think like some people working on QFT, there's some locality, right? So that cannot happen. It has some operator here, but it will excite the bus. It will excite this green part. So yeah. But it turns out that this is a genuine gravitational effect. Yeah. Okay. So just to give you some sense, how that works. So basically, you can straightforwardly understand that inside this Karl-Schwander setup. So you take some operator, on the localized on the brain inside this island. And then gravitational constraint just tells you that this operator has to be diffeomorphism invariant. So if you consider an ordinary operator OX, that won't be diffeom invariant because let's say if you take O to be a scalar operator, OX will shift to OX plus epsilon. And there's small diffuse. You will have this epsilon mu partial mu O part. So therefore, you have to do some dressing to compensate this change. So yeah. So here, in this case, this compensating can be easily visualized. By making use of this vector Goldstone field in the bulk. Because I showed you before that, this vector Goldstone field, which is this extra dimensional gravitational Wilson line, transforms like the coordinate, right? So you should just add that operator to this x inside this operator O, to compensate the translation of x. Maybe I should remind you about this transformation. Yeah, so you can see that. So this operator transforms exactly like a d-dimensional coordinate, or maybe the opposite as a d-dimensional coordinate because of this minus sign. Yeah, therefore you can add this to the d-dimensional coordinate to cancel this part. Yeah, so that is how it works. And then you can remind yourself the fact that this V operator is this line. So which connects all the way to this asymptotic boundary, and you will see that. So actually, this dressed object is a line operator inside the bulk, and it ends on the boundary. So it will source the boundary energy, basically, because the boundary is an ordinary gravitational theory. So any gravitational flux ending on the boundary can be detected by measuring, the gravitational potential. Yeah. Therefore, you can understand all of this from this simple picture intuitively. Okay. So now it goes to the second application about the statistical origin of the entropy of black holes. So the puzzle of the black hole entropy is that it seems that there are much more black hole microstates than suggested by the Bekenstein-Hawking entropy. Well, I should say exponential of that. So not A over 40 Newton, but exponential A over 40 Newton. So yeah, so because from the QFT perspective, if you take let's say you can consider an eternal black hole, you take some late time Cauchy slice, so the interior is very large. It's basically growing linearly. It's growing linearly or exponentially. Yeah, so it is growing fast with time. I forgot linear exponential. It is growing fast with time. So therefore, you can think that you can put excitations on this interior slice, and the different ways to put the excitation will give you different macrostates. But because the interior region is very large, so you can create many independent macrostates from the QFT perspective. So that will clearly violate that area law. So yeah, this is a puzzle. So how to resolve this puzzle? So basically three suggestions. So firstly, those seemingly independent microstates in the QFT limit should be overcomplete. So in the gravitational regime. So therefore, there should be a huge amount of null states among them. So once you turn on gravity. And also, to see these null states, so you really need some notion of statistical mechanics of black holes. But you don't need the UV complete theory. You shouldn't need the UV complete theory to see this, to see the existence of this huge amount of null states at least. So so because this gravitational entropy is a universal phenomenon which works for all the black holes. So therefore, this suggests that it is independent of the underlying UV complete or the UV completion of the Einstein's gravity. Okay, so we can actually crack this problem. So using the Cartman-Oberon world. So how that works? So we can start with constructing those seemingly independent black hole microstates. So using the Cartman-Oberon. So therefore, let me firstly start with an internal black hole. So which has two asymptotic boundaries. But I'm interested in the black hole microstate on one CFT. So how to go to how to obtain those microstates? You can project out another CFT to a particular state, and then so the leftover CFT would be in the black hole microstate. So so it basically works like this. So for us, we're interested in the so-called Cardi state B. So because the Cardi state, the Cardi state, in CFT you have open-closed duality. So the Cardi state in the closed channel is a conformal boundary condition, or the Cardi boundary in the open channel. And we know that Cardi boundary is due to the Cartman-Oberon. So therefore, if you go back to the closed channel, so the Cartman-Oberon will be dual to this Cardi state. So therefore, it's no longer a boundary condition, but becomes a state because of this open-closed duality. So you can project that eternal black hole. So you can project out one of the CFTs of that thermal field double state to this Cardi state. And then go through these calculations, basically because of the CPT conjugation here. So you'll see that this is actually the complex conjugate. And then so that brings B to here and the E to here, and you got that. And then you move this cat E to this left-hand side, you got this. So and then you can see that this can be rewritten simply like this. So which is like the Euclidean Hamming-Wald Cardi state on the leftover CFT. So this is the black hole microstate. The bulk picture is this. So insert this Cartman-Oberon. So this is a Minkowski picture. So a Cartman-Oberon nucleate at this past singularity, it probably is through the bulk and then ends on the future singularity. You have this dual CFT here.
But does it need to be inside the horizon? Why can't it just be outside of the horizon?
I consider the positive tension brane. You look for a solution, so it is leaving outside the horizon. So the tensionless brane is this C2 symmetry, and then you dial up the tension that goes through here.
But the tension is what from a string theory perspective? If I have some, I don't know, some ADS5 and
that's
the triggering,
that's a
the
part.
D3 will be tensionless. If I put some D3 in ADS5, from an ADS5 perspective,
That's right.
tensionless.
So
I'm a bit confused why
why
are you using a positive tension? I mean,
object
is a bottom-up object,
that's right. So
if I put this in some string theory setting, I need to I think the branes I need to use are actually zero tension.
It's basically the number of the branes in some sense. So from the dual perspective, it tells you how many degrees of freedom you have on that defect. So that is like the number of the D5 branes, if you like, in that D3 D5 case. Like the rank of the gauge group is basically on that dot. So
but I don't know how that is the tension of those.
I think technically the tension of a brane that cuts off space, because you want to throw away part of space, is infinite. I think that's what Nick said. Technically, it's a divergent. In this approximation, you need the divergent. If you want an end of the world.
But this is not an end of the world. This is really an end of the horizon, I guess.
Not end of the world. This shaded region is removed.
Oh, that's
That's removed. It's
okay.
If you are behind the black hole horizon, I'm not sure what's positive.
That's anyway.
So you got this. You got this description in the in the CFT. So which is Euclidean time evolved Cardi state. Yeah, so and you can see from here that so there's a continuous family of the black hole microstate parameterized by the tension. So basically, like you can consider different boundary states. So therefore, there seems to be much more this kind of microstates than that is predicted by the Bekenstein-Hawking entropy. Yeah, because this is continuous. Yeah, at least in this effective theory description.
Is this?
But in string theory, it's not continuous. I mean, if you look at D3, D5 boundary conditions, you know, you have a bunch of positions, you know, Antoine specified all of them. This is classified by Gauto-Witten, you know, I have some D3, ending on D5 and S5. I mean, the system is frozen. I don't have any freedom. I don't have any, I mean, the continuous parameter is an artifact of the bottom-up approach. I mean, in the top-down approach, you don't have a continuous parameter. You fix some D3 brane, you know, you have 25 D3 branes on like, you know, 3D5, 7 and S5, you put them in the right order, you order them by linking number, that's one guy, one tension. I have another bunch of branes, another guy, another tension.
Okay.
The fixed number, I mean, the brane numbers are not continuous. You cannot have 1.7 branes, you know. Either you have 1D5, 2D5, 3D5s, all these linking numbers and all these Gauto-Witten boundary conditions, and you know, that's frozen. The tension is a bottom up.
I understand.
It's not the top down.
I agree. So therefore, I will not consider this set of microstates directly, but I will consider something which might be easier to engineer in string theory. Yeah.
Is this construction related to the Balasubramanian companies?
It is. Yeah. You all see. Actually,
those are not brains. I mean, his stuff is just stuff which comes out of nothing and just.
You also see. Yeah. So actually, I'm not considering this set of microstates directly. Yeah. So I'm considering those.
But those you shouldn't call them microstates. I mean, it's just, you know, if I have a water and I have like, you know, there are some states of water where, you know, I have some water somewhere and I have some, you know, bunch of water coming in and falling out. This is the microstate of the water. I mean, you know, you put the water, you put some liquid. And then you consider some water solutions where, you know, out of these molecules, you know, some of them come up, they form some wave, and then the wave collapses back and, you know, goes back to the water. Those are the Balasubramanian solution. I mean, you know, there's something, you know, you have a uniform system, you know, there's something which, you know, comes out, and then, you know, collapses immediately. The lifetime of these null states is a crossing time. If you look at you know, what's the lifetime of the Balasubramanian branes is the horizon crossing time.
Okay.
While a microstate is supposed to live forever. I mean, I have a system of molecules in the room, so I can definitely get excitations of the molecules in the room where I have again all the molecules, you know, forming some, you know, going to the corner and then, you know, going back again. It's a very short life event, which is, you know, in a crossing time, it's gone. So those Balasubramanian branes are just some weird, weird fluctuations. One should not call them microstates of the black hole. And again, if you have water, I mean, I have water here.
What's your definition of the macrostate?
Sorry?
What's your definition of macrostate?
Microstate is something which gives me the physics of the ensemble. So something which gives me the
typical. I think you are talking about typical microstates.
Yeah, but those are not microstates at all. I mean, I wouldn't even call them microstates because, you know.
This will be microstates. So when tension is big enough, when tension is big enough, this is microstate. When tension is big enough, when this brane is close enough to these other asymptotic boundaries, so it is genuine microstate.
But the Balasubramanian guys are not. I mean, I think.
I agree.
Some excitation.
Those are not typical microstates. Yeah, but. Yeah.
How do you call them? I mean, I don't know if I have the water, if I have molecules in the room.
So
you know,
I
can force my molecules to go to the corner and then come back again. I wouldn't call it a microstate of the.
Some weird. So for me, I want to do some statistical mechanics in the Hilbert space. Yeah.
Of those.
Yeah.
Okay.
Yeah, so it is more like for example, I start with a genuine microstate, which is described by this brane very close to the asymptotic boundary. So this is one state, and then I consider some states very close to this state. So, but those states may not be typical microstates. Yeah, but they are living inside this microcanonical window. But then you all see that there's a huge amount of those states, even that they are atypical. So yeah, but then you all see that among them there should be many null states. And I want to say that there are.
This is a microstate. If all the molecules are in one corner, you have in the partition function, you have to sum over this. It will be negligible, but still it's I guess.
You still have this puzzle, of seemingly infinite many number of states than predicted by Bekenstein-Hawking. By the way, so how will I see this the existence of this null states? So I will look at this gram matrix. Yeah, so I just prepared this bunch of microstates, maybe quote unquote microstates, and then look at their gram matrix. And then from the gram matrix, I try to say the number of the number of null eigenstates of this gram, or the number of the number of the eigenvectors with zero eigenvalue of this grand matrix. Yeah, so that is what I am doing.
I here labeled by a continuous parameter. Tension.
Yeah. So yeah, if you consider the tension, honestly, it could be continuous parameter, or like you can choose a discrete number from them. Yeah, but because this range is like a continuous range, you can choose many associated ones.
So that's what you did.
Yeah, that is what I will show in the next slide. Yeah, I will show exactly so what states I choose for these I and J's. Yeah, so I'll consider this kind of state. Yeah, so I start with this genuine microstate I just described, one of them. So with a KR brane behind the black hole, maybe far behind the black hole, and then so I will insert some operator to sort of excite this state a little bit, to drive it slightly away from itself, but still inside this microcanonical window. But this operator is holographically dual to this shell from Subramanian's and others paper. And then so I'll just smear this a little bit using the Euclidean time evolution. So yeah, so if you calculate the norm of this state, so this is the bulk geometry. Yeah, so this is the bulk geometry. So whose exponent? So if you calculate the on-shell action on this geometry, take the minus exponential, you got the norm. Yeah, so this is the geometry. Yeah, so here you have this blue end of KR brane, and then so you have this red shell, so which is described by this OI. Yeah, so if you do that calculation, I will get this result for the norm. Yeah, for each state. But then for us, we're interested in the inner product between different states. So that is JI1, I2, for example. Yeah. So how should we proceed? So we'll see that. So actually, we'll calculate the higher moments of this grand matrix. So yeah, so for example, so we can consider these particular higher moments, right? And then so it turns out that the bulk geometry that calculates these higher moments, the connected part of this higher moment is this wormhole geometry. Yeah, this wormhole geometry fully connected, even though we have different copies, but they are fully connected in the bulk. You have these wormhole geometries. And then the on-shell action from this wormhole geometry is simply exponential some power of the Bekenstein-Hawking entropy. Yeah, so this is the result, so which will be important for us to extract the number of the null states. Yeah, so how to extract the number of null states? So I consider this standard technique in random matrix theory, which I think is firstly introduced into quantum gravity by Pennington, Stanford, Schenker, and Yan. Yeah, so I consider this resolvent matrix, and then so from the trace of the resolvent matrix, I can get the so-called spectral density. Yeah, and then so from here you can see that the null states of this grand matrix G, it actually corresponds to the delta function piece of this spectral density rho. Yeah, so therefore, our goal is to calculate this spectral density rho from this resolvent matrix and look for the delta function piece. Yeah, so the coefficient in front of that delta function piece is the number of null states because of the trace we take. Okay, so now you can try to find this resolvent matrix by working on the Schwinger-Dyson equation and solve the Schwinger-Dyson equation. And then you use that previous result about the fully connected higher moments. And then we will see that the result is given by this. Yeah. Yeah, so and then you can take the trace. You can take the trace. And then I consider omega. I consider omega states. Omega states which are omega independent, the independent states in the QFT regime. Yeah, so that is this big omega. And then we'll eventually see that the number of independent states is reduced from omega to exponential Bekenstein-Hawking entropy. So yeah, that is what we want to do. Okay, and then so from that resolvent matrix or trace of the resolvent matrix, you can solve this rho, and then it turns out that this rho has this delta function piece. And you can ignore this delta function part, which just tells you that when omega is much bigger, when omega is bigger than the black hole, the number of black hole microstates, so this will be clicked. So, and then this coefficient is the number of null states. And then so therefore you can see that the actual number of independent states is omega minus the number of null states, which is exactly exponential of Bekenstein-Hawking entropy. Okay. Okay, sounds good. So now it brings me to the third application. So the third application is about the global symmetries in quantum gravity, the absence of global symmetries in quantum gravity. So yeah, so the standard argument of the for the absence of global symmetry is a little bit shaky for me. So therefore, I would like to reformulate it in a slightly more precise language. Yeah, so for that purpose, let's consider an eternal black hole in ADS, which is described by this Penrose diagram. And we assume that there are some global symmetry, so acting on this theory, and then with light charged particles in the bulk. So particles are these particles are very light, so whose gravitational back reaction can be ignored, but then it carries they carry global symmetry. And then so we can go to first we go to Layton Cauchy size. And then so from there, so we can put any number of particles inside this interior part. And then so from that, so we can construct a distinct charged black hole microstates. And then so this differently charged black hole microstates, so they are genuinely independent state because of the assumption of the existence of global symmetry. So they carry different global symmetry charges. And then so again, you will see that so there's a tension between that consideration and the Bekenstein-Hawking entropy of the black hole. Therefore, this suggests that there cannot be global symmetry in quantum gravity. Yeah. So but for us, so we want to understand the reason for the absence of global symmetry. Therefore, that previous consideration is just suggestive, but you cannot extract a crispy statement of conjecture from it. So therefore, to try to extract the crispy statement of conjecture, so let's do some further consideration. So there's another implication of the Bekenstein-Hawking entropy bound, which is a holographic principle. So that is reformulated as a so-called central dogma by this group of people from the Institute at Cornell. So it basically tells you that so if you look at the black hole, let's say in the usual ADS-CFT case when there's no mass, so it is described by a quantum mechanical system, so which has this number of degrees freedom, or the exponential of that number of degrees freedom, and which evolves unitarily under time evolution. So therefore, black hole is really a unitary quantum system. So therefore, from here we can see that a crispy statement of conjecture is that so the absence of global symmetry is tied to unitarity of quantum gravity. So this is a good statement of conjecture. But then the question that so this conjecture is very weak. So how could we make some progress to this conjecture? So therefore, I will not directly crack that conjecture, but I would like to consider a slightly opposite question. So what if I break the unitarity in a controlled setup and see what's going on? For that, so we can again consider this island setup. So we are couple this black hole with the bus. So because of this coupling, so this black hole, this gravitational black hole is no longer a unitary quantum system. Yes, but of course the union of this black hole and the bus is a unitary. The subsystem is not unitary. So therefore, from here we see that so unitarity is broken, and hopefully we should be able to see some global symmetry in this setup. If unitarity is really tied, if the absence of global symmetry is really tied to the unitarity. Break the unitarity, I should see the appearance of global symmetry.
Fake global symmetry from the perspective of the lower ADS, of the brain world ADS. It's not a full. I mean, if I embed this in string theory, it's not a full global symmetry, but it's something which looks from the perspective of the quadrantal theory to be a global symmetry.
Well, I would say it looks like global symmetry in this picture.
Sorry?
In this picture, yeah.
Yes, for the
in intermediate description.
Yes,
yeah,
intermediate description.
Yeah.
Okay.
Yeah, that's
Okay.
right.
Good.
Yeah, oh yeah, that's right. Okay, yeah. And also we know that, so for example, so the information in the island I is encoded in the boundary, in the spot subregion, which claims the island. So therefore, hopefully, so we should be able to construct some operator inside the island I. So we should charge under some global symmetry. And that global symmetry charge should be measurable in the bus. Yeah, so that is the construction we want to do. We want to construct an operator inside the island, so which carries global symmetry. That charge can be measured by this bus subregion. So that is the construction we want to do. Yeah, so we can see that from here. Yeah, so the tension between the global symmetry and Bekenstein-Hawking entropy bound is limited in this setup, as I just explained. And our goal is now to explain this construction. Just for the sake of simplicity, so I'll explain that in the Cauchy-Brun walk. But I should say that so that construction can also be done so in this intermediate description directly. So to do that construction, so again, I have this nice Cauchy-Brun walk setup. I have this warp factor, Cauchy square rho. And I have a Cauchy-Brun. I have this asymptotic boundary, which is fast. So I want to turn on a Maxwell field inside this ADS-D+1. So in other words, I turn on gauge symmetry in the bulk. Yes. So therefore, I can do the same analysis as I did for the graviton to this d+1 dimensional Maxwell field. So I'll firstly separate the component, separate the d+1 component into d component, so which is a vector field in the ADS-D perspective, and the scalar component, so which is the line object, which is the gauge Wilson line. So yeah, you start from the point in the ball, you do this integral all the way to the asymptotic path. So this I call theta. And then I can perform the KK decomposition. And then so from this vector part, you will see a tower of KK photons. And then from this scalar part, you will see a tower of KK Goldstone bosons. Same phenomenon as in that graviton case. Yeah. And then so for the same argument or the same properties of the bulk as in the graviton case. So the massless mode, for this photon is normalizable because of this infinite actual dimension orthogonal to the brane. So therefore, the physical modes are all massive. And then for each of the massive photon, you have an associated Goldstone boson. Yeah, so as the KK component of this Wilson line. Yeah. Yeah, so these are the key features. Yeah, these are the key features of this setup. Okay, so to see the global symmetry, so let us remind ourselves that so in the usual ADS-CFT correspondence, so if you have some gauge theory, you have some gauge symmetry in the bulk, so that should be due to some global symmetry in the CFT, and the holographic relationship between that gauge theory in the bulk and the global symmetry charge on the boundary is that so the flux of the gauge field through the boundary is actually the global symmetry charge. So therefore, so that same consideration applies here. Yeah, so you consider the flux of this bulk gauge field, the electric flux through this asymptotic boundary. So that is the global symmetry charge in the bus. Yes, and also you can remind yourself about this canonical commutation relation between the bulk photon field and this particular component of the electric field. Rho is really this direction, perpendicular to the brane and then perpendicular to the asymptotic boundary. So we constructed that Goldstone boson from this A rho. Remember, so theta is the Wilson line. So in these actual dimensions, therefore theta is a line integral of A rho. And then from here you can see that so the theta field, so the Goldstone boson would have a non-zero commutator with the electric field of the bulk. Then that tells you that so the Goldstone field will have a non-zero commutator with a bus global symmetry charge. And then so you can do the calculation. So this is the result. Yeah. So the bus. So yeah. So so the global, the Goldstone boson is actually charged under the bus global symmetry. Yeah, so and then so you can consider some charge operator on the brane, and then charge operator on the brane, then so you should impose the gauge constraint as before, and then so you should dress that operator on the brane. And in this case, that operator on the brane shouldn't be dressed using the brane using the brane gauge Wilson line, because that Wilson line, if you start from this point on the brane, you dress it using the brane Wilson line, it will go outside of the island to this asymptotic boundary. Therefore, the dress operator will have some charge which can be measured here. So that is not consistent with the holographic interpretation of the island. Therefore, you should dress it using this Goldstone boson theta. Yeah, so the dress operator is again like this. It's like this line object which ends on this asymptotic bus. This is really the reason why. So why the charge operators in the brane can be measured, or that charge can be measured on the bus. Yeah. So the dressing is done using this theta field, and theta has a non-zero commutator with bus global symmetry charge. Therefore, from here you constructed a global symmetry charge operator inside the island. So although in this Cauchy-Brane world, it looks like a gauge symmetry in the bulk description. But if you consider this genuine intermediate description, then there's no actual dimension in general. There's no semi-classical actual dimension in general. Therefore, this is a genuine global symmetry. Yeah, from this intermediate description perspective. Yeah, and then now you can go back to the picture that you have some black hole on the brane, and then so that black hole will have these hairs. Hairs are just these Wilson lines, and then they are dressed to this bus. So we call this white hair. Yeah, because it's dressed to a bus. So okay. So now how many minutes?
Fairly soon because we're running up to the hour at this point.
Okay. Can I try to take another 5 minutes?
Yeah.
Yeah, that's right. Yeah, I think these last two applications, I'll only briefly explain this. Yeah, so for the fourth application, we want to understand the quantum origin of the gravitational spacetime. In other words, how the gravitational spacetime emerges from some underlying quantum description. Yeah, which is basically a sharper statement than the ADS-CFT correspondence. It's like, so how could you derive the gravitational ADS directly from the non-gravitational CFT? So that's the question we want to understand. So yeah, so some early suggestions in the literature is the so-called ER equals to EPR conjecture. You take two non-gravitational CFTs, you in the entangled state, for example, in the thermal field double state, the bulk dual is a semi-classical gravitational geometry if you tune the CFT parameters properly. And then this is the ER equals to EPR conjecture. Yeah. So this is a early suggestion in the literature. But the question is that, so, but the problem is that, so it only works for black holes. But what about the states that we are primarily interested in, for example, which closely models our universe? So those states are, well, for example, a good state of that is the empty ADS. Yeah, because our universe is globally not crazily excited. It should be captured by some states very close to the ground state. Yes, therefore, the question is that how could an empty ADS emerge from the CFT? Yeah, so a few observations. Firstly, so if you use the standard ADS-CFT correspondence, that should be dual to the ground state of the CFT. So therefore, the question is that how could you start from the ground state of CFT to derive the existence of this ADS? Yeah. So therefore, you can try to correct that question by making the following observation. Yeah. So the ground state of the CFT is maximally spacetime symmetric. So therefore, there's a huge amount of entanglement inside this state between nearby patches. So therefore, if you borrow the ER equals to EPR consideration, you'll see that this strong entanglement should be dual to some higher dimensional gravitational geometry. So that's the intuitive picture, but how to realize that? Yeah, so that's the question. So yeah, therefore, we should try to leverage on this entanglement. Yes, I won't have time to explain all the details, but I will say roughly how we realize this entanglement. Yes, and hopefully and then the next step will be very obvious. Yeah. So firstly, to see that entanglement, so we want to start with considering a path integral, Euclidean path integral, which prepares this CFT ground state, and then we regulate that path integral by putting very small Cardy boundaries. Yeah, here and here. So therefore, by that I cut this CFT state into small pieces. And then eventually I should shrink the Cardy boundary to 0 because they are just regulators. But then the interesting thing that, so this the existence of these Cardy boundaries tells you that, so there's some local notion of temperature. Yeah, so locally it is like a Rindler patch. Yeah, it's like you go from Minkowski patch to Rindler patch, right? Locally, it is the same thing. And then when you shrink that to 0, so that Rindler patch temperature is very high. So therefore, so from this consideration, you can see that you got many small pieces of CFTs. They are living on intervals, and then they're actually in a highly entangled state. And then you can study this state. You can study the path integral preparing this state, and then you can see that. So that path integral, you can derive an emergent ADS3 geometry directly from that path integral. Yes. And also I should say that, so this is actually equivalent to many entangled black holes. So in the eternal black hole case, you have two black holes which are entangled, but now you have many small intervals. So each of them, you should think of it as a black hole, and then they are all entangled. So therefore, the bulk picture is really like an entangled many black hole states with Carr-Channel brains. Yeah, that's the bulk picture, which we actually successfully derived. So our result is that, so we can derive this emergent geometry directly from CFT for 2D CFT. And then also we can prove the RT formula in general cases, multi-intervals, arbitrary bipartitions, without assuming any replica, symmetric pattern domination, etc. So everything is derived from the CFT. And then also the spacetime is a result of this black hole or wormhole condensation. So which is actually the mechanism for the emergence of the gravitational spacetime, or how the ADS-CFT actually works. And also, so another way to interpret our result is an exact tensor network description of the spacetime geometry, which has been a dream for the holographic community for many years. And then, so this tensor network is no longer a simple model, but it is the tensor network, so describing the gravitational ADS. Yeah, because this is exact from the CFT. Yeah, so yeah, I encourage you to read this paper. So which are clearly written, although It is a little bit intense in the technical aspect, but we try to write it in a very clear and coherent way. So yeah, hopefully you can understand what all.
We should finish imminently, please.
Oh yeah.
Yeah.
2 minutes, 2 minutes. Yeah. 1 minute, 1 minute.
Maybe, I mean, we can, I mean.
Oh yeah, we can discuss.
I think we can just, I think we can, no, I think we can skip 5, I mean, you know.
Oh, we can skip 5.
Question, when is lunch cut off?
Okay.
Quite often they have a talk at 2:30, so, I mean,
No, I mean, is
There's
lunch
less-
gonna shut down in the canteen at 1 o'clock?
yes, I think at some point it will shut
Yeah,
down,
but
so.
we need.
So maybe
Okay.
one universities we can leave.
Yeah, one.
we can leave
Yeah,
the-
let me say one. Let me just say one sentence.
Okay,
Yeah.
you might be depriving people of their lunch, so.
Yes.
Oh, okay. Yeah.
So, I mean.
Yeah. So just one quick sentence. So yeah. So yeah. Okay. People can wrapping up while I'm speaking. Yeah. So yeah. So some recent work in the literature, for example, from Edward Wheaton and friends, they suggest that in a closed universe to have in a gravitational closed universe to have non-trivial physics, you have to add an observer. So yeah. So I want to say that this is really another way to see the massive island. So in the island case, we see that to have island, you need gravitational mass. The gravitational mass should be really understood as an observer. Yeah, that's it. Yeah, anyway, so conclusion is the same as the messages I want to convey. Yeah, so here are the references. Thank you very much.
Maybe one question or two.
One
or two.
or 0? Okay.
Okay,
We'll meet in 3 minutes up.
okay, sounds good. Thank you, thank you, thank you.